young ladies, young women, I should say. You've done an amazing job over the last 3 days. Um, whichever institute I think you're from, I don't know, but they're doing a good job. I think we should give a round of applause for them also. Um, and thank you also to MTA, Janaki, and everyone else who was involved for the invitation. Um, this is a very important, I've always thought that this kind of initiative is very important because if we want mathematics to be relevant, if we want mathematics teaching to be um, excellent, then these initiatives are needed. So thank you for the invitation. And I will mainly start with, why I'm choosing this presentation and sort of some background. Um, if I think about why I chose mathematics as a career, or even why I like mathematics, and if I think back to my childhood and experiences, the first exposure to mathematics, um, there are two that stand out. Um, and both of them happened outside the class. I mean, it's unfortunate that I can't remember my earliest sort of childhood memories of mathematics. The ones that excite me were both outside the classroom. The first one was um, sort of a book that I saw. I couldn't understand the mathematics, but there were two pictures in it that fascinated me. And one was, um, it was on topology. So one was this coffee mug that slowly deforms into a donut. You may have all seen that. So it was fascinating sort of to see what is happening there. And the second picture was of a donut, of a Mobius band, a big Mobius band, and two people, one with, I still remember that picture, one with a can of red paint and one with a can of blue paint, trying to paint what they thought were the two sides. So one was painting it red, the other was painting it blue. And then the second picture where they meet and they realize that what they thought were the two sides uh, was actually the single side. And so that picture had the two of them, throwing the paint cans in the air, sort of in a show of amazement. And I thought that was very cool. Um, I didn't understand anything as to why that was the case, or what Mobius band was, but I thought that picture was cool. The second experience was, I don't remember what class I was in, maybe sixth. What grade is Pythagoras theorem taught now? Seventh. So I was, I think, in sixth that day. And we had just finished our final exams for the year. My brother and I went to the same school. So we came back and it was like a chutti hai, do mahine ki or whatever. So we came home and we were playing in the yard. And my brother, who was a year ahead of me, he said, "You know what you're going to be doing next year in math?" I said, "What?" He said, "Pythagoras theorem." So I said, "What is that?" And he took a piece of stick and drew the picture on the ground. There was some dirt there, the right triangle, and did the three squares along the edges, and proceeded to explain Pythagoras theorem to me. Again, I still remember that picture very clearly. I may not remember all the details of the proof he gave, but so for me, mathematics was never confined to a classroom. So what I'm about to illustrate here is an initiative. When I joined IUSC, there was no math department, so we started a math department. But very early on, this initiative was designed to encourage students towards mathematics and ensure that they don't see it as a scary thing. So we started with a program called Impact. I'll talk a but let me begin. This is not moving. A lot of technical issues today. So, the first question I wanted to ask is how do we see mathematics? And if we say we means us mathematicians, then uh, you hear all the good things. Mathematicians wax eloquent about the beauty, the elegance, right? The creativity. I've just put three of them here. But everybody loves mathematics. Now ask the students, how do they see it? A confusing jumble of formulas generally. Ask students in general. This is the first impression they have of mathematics, not of anything elegant, not of anything beautiful, generally. Um, and this is not unusual at all. I don't know if those in the back can read it. It says, who is putting all the math books in the horror section? This is librarian art. And many of us are guilty of this, where a teacher will say, I expect all of you to be independent, innovative, critical thinkers who will do exactly as I say. And I must confess, there have been times when I've done that also. This picture to me represents sort of a summary of what I just said. That if you look at the top of this is a hyper, sort of a three-dimensional version of the hypercube. It looks like a jumble, but if you look at the shadow, it's quite beautiful. So I think of this picture as representing mathematics teaching and mathematics in general. It's actually the beauty is hidden. You know, at first when you see it, it looks like a sort of a confusing jumble. So what do we do normally in classrooms? We think our job is to give information, which is important. We have to provide all the facts, the formulas, the algorithms, and student is expected to then regurgitate that in the exams. Um, and obviously, and that encourages rote learning and so on. This happens. One of the questions, and this has happened to me a few times, is I'll be in class and teaching something, and then I think of an idea that this will take this a little further. So I'm very excited about it, and I'll give them the example and show them something. And I think like this is wonderful. And then a student raises his or her hand and says, will this be on the exam? This is like the worst possible thing that can happen to a teacher because our teaching is often test centric. Students think that everything will be on the exam. If a teacher is explaining, will I have to memorize it? Will I have to sort of repeat it as is done by the teacher? I had an incident once where my niece, when she was very young, class 4 or class 5, she came to me and said, there is this math question, and my teacher did it in class, but I'm confused. I don't understand the solution. So I looked at it, and there was an error in the solution. So I explained the solution to her, and she understood. And then she said, no, but I have to, in the exam, I have to write what my teacher wrote, because otherwise marks cut jayenge. That was the answer. I said, do you understand the solution? She said, yes. I said, well, I don't care what you write on the exam. But there are students who feel that if I write something else other than what the teacher has said in class, marks cut jayenge. So a good student is one who develops good procedural fluency. And this is sort of, I'm generalizing, there are exceptions, of course, but I'm sort of saying, generally speaking, that's how classroom teaching goes in many areas.
What is of value? I mean, what do we want our students to learn? We want them to have I'm just putting a few here. They should be able to, in mathematics, it's very important to be able to see patterns and relationships, analytical skills, creative thinking, critical thinking. We all talk about. And also, they need to be able to communicate their ideas. In mathematics, even more so in a very concise way, they should be able to do that. So if we talk about creativity, it thrives on experience. If we don't give them the opportunity to get their hands dirty, they're not going to learn the same way. So can one create space for providing right mathematical experiences and exposure to sort of genuine mathematical activity and reasoning? It doesn't have to be sort of high-fi and very high-level mathematics, but something simple that will allow them to um, understand some even more profound ideas, but in a very simple setting and relaxed setting. So that's how we started our impact program. 2012, 3 years into the department came into being in 2009. So just 3 years into um, the existence of the department. And the idea was math outside classroom, hands-on problem solving, and we would have initially it was like half a day. We would bring the students from different schools into our campus and create little activities for them, group work. There would be a presentation and there would be a little competition also. Um, and we did it, I think, for about 3 years or so in that setting. And then we thought, well, we're only catching a certain group of students who are living, in and around the university catchment area, maybe Srinagar. Our university is about an hour away from center of Srinagar. So what about students who are in far-flung areas? So what we did was the concept of math festival was formed. My The purpose of my presentation today is just to give you some ideas. Maybe some of you can go back and replicate them, or change them according to your own setting. But to illustrate that it's actually very easy to do that and with very minimal resources. So the idea was that we can go, rather than invite students to our campus, we can actually go to them wherever they're living. And we were choosing areas which are sort of outside the urban zone. And so math at the doorstep. We made it much more sort of creative. I can't see the. No, but I can't get the. It's not. This thing is. Laptop or this? No, this is on. यही बंद हो जाता है. Maybe you could tell us more about the program you were describing. Yeah, so we have done it in areas like Kupara, which is really like 3 hours away from Srinagar. We have done it, so north area of Kashmir, south area of Kashmir. In Kupara, which is even farther away from Srinagar, we had our largest audience. We had almost 300 students who had all gathered at one of the way we do this is we go whatever area we choose, we contact one of the local, either a school or a college if there is a college nearby, because we need some premises where we can hold the event. So all we need from them is space, essentially, and to be able to reach out to schools in their area so that they can invite the students. So we ask for space and for like tables and chairs we may need for our festival. Rest we bring with us. So a team of faculty and students from the department goes out. We have a group of students, some of them undergraduate, some of them graduate students. We take them with us. And what we do is the whatever venue we're at, we put some tables. It's like a where you have, that's why we call it a festival, that there are, we set up tables and each table will have some topic in mathematics. So there will be at least one faculty, maybe two students on that table. They will have all the relevant information. There's a laptop there if you want to show them videos and so on. And we put some easels and then some sort of information on the easels, all very, there's usually not a single formula on any of those slides or anything. And we have a lot of toys on the tables. And so it's very interactive. So I'll give you some examples of what we do. So we also encourage the students, our own students, to be the main facilitators. They're the one answering questions. They're the one illustrating whatever concept needs to be illustrated. And one of the sort of the byproducts of this has been that our own students love this experience. They're always asking us, when are we doing the next one? It's a very enjoyable experience for them also. So some of the topics that we have chosen for the math festivals: topology, or we'd say rubber sheet geometry, fourth dimension, estimation of pi, clock arithmetic, which is, modular. Math and art and craft, this is always popular also. And soap bubble, the last one is my favorite. I always make sure I'm sitting at the soap bubble table so that I can blow soap bubbles. Um, so in topology, Mobius band is a very popular topic. What you can do is you make Mobius bands out of paper and then have a scissor and then illustrate. For example, you can cut the Mobius band in the middle and ask them how many pieces will we get and how many do we get. Has anyone ever done it? If you take a Mobius band and cut it straight in the middle, you get only one piece. But then you very slyly slide the scissors next time to the right or to the left, and then ask them again, how many pieces will you get? And you get two pieces, but linked, right? So it's like a magic trick for them. So then you can explain in simple terms. Klein bottle, obviously, you can illustrate it with pictures, not theory. One of the fun elements in not, just to illustrate some of it, is you put them in handcuffs. There is you link two people together and then tell them to unlink themselves. That's also a very fun activity, which is the one on the left side. Like you have two ropes tied to one, each person has this like a handcuff, but the cuff is linked in the middle, and then they have to figure out how to unlink themselves without cutting or without untying the knots. And then this is one of the things we do, the my childhood picture. And this is an illustration from photograph was taken in Kupwara. So this is like the remotest area we've been to. And as I said, we had close to 300 students over there. It was overwhelming to see the response. And they had come from all the sort of the regional schools. And we had to, because of the numbers, we had to sort of bring them into the hall in groups because we couldn't accommodate everybody. So we had to then repeat the exercise after like an hour or so. So some of the toys you can see here, we take that Play-Doh and make the models out of the coffee mug and becoming a donut. And then you have a lot of braids also for them to figure out how we braided them, topological braids, and then Homi's band and so on. This is also a very popular topic, illustrating how one can imagine the fourth dimension. So, in order for them to understand the fourth dimension, you start explaining to them what a cube in zero dimension would be like, then a cube in one dimension, two-dimensional cube, three-dimensional cube, right? And then a representation of the four-dimensional. And this becomes a way, like the picture on the bottom left, we illustrate that this is actually not a three-dimensional cube, it's a picture of a three-dimensional cube. So the same way when we have a model of the hypercube, the four-dimensional cube, we say that it's a picture, three-dimensional model of the four-dimensional cube. And you illustrate also how you go from one dimension to the next. How does the cube change? For example, if you take the one-dimensional cube and slide it, you get the two-dimensional. So the act of sort of sliding it into the next dimension. Same thing, you take the two-dimensional and move it forward, and it gives you the three-dimension. And that's the action that happens here. You take the three-dimensional, move it into the fourth dimension, and you get the. So there are different ways we illustrate this. I'm just giving you a flavor. And also what the unfolded cube would look like. So the unfolding four-dimensional cube is at the bottom, but you illustrate the idea using the three-dimensional cube. And if you unfold it, what would it look like? So that's something they enjoy. Um, so we have models of the various cubes on the table, and then they can look at them and figure out how this thing works. They can slide it and so on. We also have the unfolded cube. By the way, this student of ours, I'm happy to say, he at that time was just starting his master's with us. He has studied his undergrad with us also. He is now doing a postdoc in Canada. So just recently he joined. Um, so this is like we had a local carpenter make this um, the unfolded hypercube. I thought he did an amazing job. He understood the concept in like 2 minutes and made it. And these were done by a local um, ironsmith. These are made of iron rods, and he welded them together and made all the in the back you see the hypercube and then all the others. And zero dimensional, we got some little iron bead. So everything was done locally. We didn't have to buy anything. Estimation of pi. Again, we have a lot of pi jokes on those slides. Uh, and has everyone figured it out? I ate some pie and it was delicious. Right? So that kind of stuff. And this is one way of estimating pi, the simple one. If we have students who are much younger, you take a round table, put some cookies on it. So they count the number of cookies along the circumference and then the number of cookies along the diameter. It's a rough estimate, but if they can calculate it correctly up to at least 2 digits, they get to eat the cookies also. Um, but if we have students, and for students who are a little older, then we can do the Buffon's needle problem. And we often then also show them a simulation of it where the number of needles can be large, and then they can see the approximation is better once you increase the number of needles. But this is easily done. You'll see it in the video later. So we actually get the matchsticks, and then we have a big sheet, and they throw them on the thing. So again, the idea is that it should be hands-on. The other topic is the modular arithmetic, so barcodes and check digits. Uh, Another fun part of it is that our own students made these clocks and they use their own creativity. So the idea was if you want to illustrate modular arithmetic, we often ask them, is 9 plus 4 always any figure like that? Is it always 13? And they say yes. And then you take them to a clock and say, okay, if it is 9 o'clock now, what would the time be 4 hours later? So then they realize that it's a different way of adding. So then instead of a regular clock, you do other clocks. So these two were done with modulo 10. Do you have a question? Uh, so, and the students volunteered to make these clocks, and it was sort of enjoyable for them also. These are our own students who made them. Math and art is also a very popular um, topic. So tiling, and then we also go to Penrose tiling and we show them some videos on it. Escher, they can actually sit and make some Escher tiles. It's very easy to illustrate to them sort of how you do some basic. It looks very difficult, but when they see the process of making the Escher tiles, it's actually not very difficult. Uh, and then how it is used in arts and crafts. And we try to relate it to the local crafts. So whatever idea, symmetry, deflection, rotation, then we try to illustrate it in terms of the local and regional. So as I said, there will be all these. This is just from one of the ones where we have the concept of perspective, viewing distance also, and Escher, and then some of the other stuff. And this is one of our students also. She's working here in Delhi now as a lecturing. This is Faiza. Again, some local crafts and sort of these are the lattice windows that are very common in Kashmir. So you can illustrate some of the concepts of symmetry using those. And as I said, we have um, laptops on all of these tables so they can sit and also watch some of the videos and see how it is done. So bubble math, my favorite. My favorite table to sit at because you actually get to blow soap bubbles. So they blow the soap bubbles and then you ask them about the shape of the bubble. Why is it spherical? But before we even do that, we give them some examples. And in Kashmir, everybody is used to cold weather. And we ask the question as to why do we sort of curl when it gets cold, we tend to do this. Why is that? And you also see animals do that, not just humans. And then you get to talk about why are we trying to do this? And the idea is we curl ourselves into a ball when it's cold because we're trying to minimize, they can get that idea that we're trying to minimize the surface where, we're exposed to the cold. So then we talk about surface area and minimal surface area. And then isoperimetric theorem that the minimal surface area will be when it's a sphere. So that then they understand why the soap bubble is um, round. Then we go from there to the honeycombs. So why are they hexagonal? And these are two things that they can understand. I mean, they see in real life also. It's not something, but you talk about bees that bees know mathematics, and the concept or the idea is very intriguing for them. So then you talk about, so from one soap bubble, you go to the idea of what happens when you combine two soap bubbles or three soap bubbles. So what are the conjectures? Obviously, the one for two has been done. The angles have to be 120 in the two-dimensional and in the three-dimensional. But the three soap bubble one, as far as I remember, is still a conjecture. Um, that it has been shown for two that if you have two soap bubbles, this is sort of the shape where they meet, the angles have to be 120, the middle one is sort of this. But if you have three soap bubbles, then That is the conjecture that the angle will remain the same. It is still a conjecture. But they can then understand, okay, what happens when we have lots of soap bubbles and then they begin to look like these hexagonal cells. And then you have the beehive. Those of you who may not know, the way the bees make we showed them a little video of it, but the way they make the cells is itself fascinating. The idea, if you haven't heard this before, but what is the idea of the hexagonal cells? That the um, the conjecture which I mentioned, in the previous, the honeycomb conjecture, it was a conjecture, but it's no longer a conjecture now. Um, that if you take the plane and you have these cells or tiles, and you want the perimeter to be, if you look at the perimeter of all the cells, boundaries, you want it to be minimal, but you also want the area within them to be as much as possible. That gives you the honeycomb shape. That was the honeycomb conjecture. So the bees want the cells to hold maximum volume, which is the honey, because they have to store the honey. But the cells are made of wax, and they have to work hard for the wax. So they want the wax to be minimal. And so but the way it's also fascinating the way they actually make the cells. That when they start out with the wax, the back of the bee, if you remember, is sort of round in shape. So they use that to poke through and make this round shape. Then apparently they beat their wings or something. It creates heat. So this wax starts to melt, and it turns into this hexagonal shape, which is fascinating. So this is one other, um, one of the other activities. Then we also often do some presentations, and we show them several videos also. But this is a very popular topic. We call it the girda problem. Girda is the Kashmiri word for this bread. It's a local bread, very tasty. Usually comes in the small shape. In those days, when this picture was taken, it was 5 rupees for the small one. Now, just last week, the price has gone to 7. So now I have to change this slide. Um, but this made it easy. You could get a 5 rupee one, you could get a 10 rupee one, and you could occasionally also get a 15 rupee one, which was much bigger. 5 was the more common, and 10 you can get sometimes. And if 15 rupee one was usually special order. Yesterday, Professor Ramanujan was talking about Pythagoras theorem, and that if you take the right triangle and look at the three sides, you don't necessarily have to use squares, right? You can use any other shape, and somebody says semicircle also, and then in fact any shape, and then you have similar copies, larger or smaller copies of that. So we do that with this Girda problem. We ask the same question as to if you have the Pythagoras theorem. Well, the question starts with this, that if you have a 5 rupee, the kandur is the Kashmiri word for the baker. So if the kandur has a 5 rupee, 10 rupee, and 15 rupee, which one gives you the more bread? This option that you buy the 15 only, or you buy one 10 and one 5. Um, Technically speaking, the bakers make their bread by weight. They have to ensure that the 15 rupee one has the same weight of the flour as 10 plus 5. But to make it interesting, we're doing it by area. And they can relate to, they eat girdas every morning. It's a very popular bread. Um, so how do we know whether we're getting more bread with option 1 or option 2, whichever we choose? So then we illustrate this with the use of Pythagoras theorem, where um, if the angle, so you cut each one in half so that you're creating a semicircle, and then you form a right triangle out of it. If it is a right triangle, then either option is okay. If the angle is more than 90, then the hypotenuse, the area on the hypotenuse will be more. So then this option, um, so then this option is, what happened? I can't use the, oh, there it is. Yeah, no. Um, so, well, let me just put it up there. But this is how we, this is an older picture. You may not recognize me, but we actually, we actually cut the gildas out. And then they can see in this case, it looks like a right angle to me. So the Gandur was doing his job properly. He hadn't cheated on the gildas. We get some local Gandur, the baker, to actually make the three sizes of the gilda. As I said, the larger one is not always available. And then you also get to eat it at the end of the presentation. But it's a good way to illustrate a concept to them without making it sort of too much with formulas and explanation. They see they can understand that why the Pythagoras theorem. What Jam was saying yesterday, that if you have x squared plus y squared equal to z squared, you can multiply it by any constant. So that becomes the scaling factor. Um, so then it works for this as well. Um, and these are some of the sort of the ideas that I don't think I can show it here. Some of the ideas that we do in this math festival. We also have on occasions done a group exercise with them where we divide the students into groups and we let them discover some theorems. One very popular topic was the Euler formula. You allow them to make some graphs, count the number of vertices, the faces and edges, and then figure out what the formula is. And if they, do this, it takes about an hour or so. Again, our own students act as facilitators um, for each of these exercises. I think I want to leave some time for, I don't think the video will play here, but I started with some quotes, so I should end with one. Sometimes the questions are complicated and the answers are simple. And that's where I want to end. Thank you. And I'll show you a video. Thank you. Oh, अच्छा. Apologize.
Thank you, ma'am, for this wonderful session.
I have a video to show. Uh, the video will illustrate to you how much fun it is for us also. Forget the students, but it's also we get to go to all these lovely places which are. So this is a reel for one of the more recent ones we did. Should I? Yeah. This is how they walk. So this is a short reel. We had done this in an area, remote area in South Kashmir. We got there is a college nearby. We got them to host us. Again, the host institution doesn't have to spend anything. We only take their space, whether it is an outside area or something. We do need like a slide, PowerPoint or something. So we need to have audio visual support there. But that's essentially and then tables and chairs. That's essentially all we need from the host institution. In terms of the resources that if you do this in your own schools and so on, it's very minimal. Pencil, paper, printing of the various things. You will need some easels, which are not very expensive. You buy them once and then you can reuse them every year. Um, and then laptop, you carry your own laptop with you and you can show them the videos because it helps in illustrating some concepts. But the expenditure on any of these events is not very high at all. You don't need to, if you're doing it in your schools, you don't need to go somewhere else, right? You can do this in your own school, maybe once a year for one sort of cohort of students. It will take half a day um, if you're doing it within your own institution. Um, and as I said, minimal resources, so your bosses will not be too unhappy with that, that you don't have to get approval for X amount of money. Very easy to do. And I hope something from here has encouraged you to replicate this idea. You can have, I mean, I've just illustrated 4 or 5 topics, but these are not the only ones you can do. These are what we have done, but there are many others. Thank you very much.
My father, is actually waiting quite long here to hear this particular talk. We try to get into our university to do this, in fact, to do this activity with our students and those students. And that's exactly when the COVID lockdown happened.
Yeah.
It happened to start exactly when we were trying to get over to our. Any questions?
Yes,
Mike.
I can stand over there. Here.
There's another mic. Take this, go to just last. Yeah. You can stand and speak so we can see you.
Less of a question, more of a family you can think of it. That I love the project that you've been carrying on. Thank you. I'd like to know that in case someone, or in this case me, would want to know the details of the activities or the other factors, do you have some website or something which gives us a little more insights about it?
Absolutely, I can share. If you can get my email address from anyone here, Amber or Janaki has it. Just send me an email, anyone else in the room also, and I'll share it with you. We have a lot of these, like some of the explanations come from the slides we put on the easels. You can use them. Any other questions if you wanted to do this in your own institution, need some guidance, help, or have questions, feel free to send me an email. Oh yes, we have a whiteboard. I forgot. Yeah. I'll write it in uppercase so that everyone can see, but it's all lowercase. So it's my first name, last name at Gmail.
Yes, one word. I do the laptop.
This is going to fall down. Is it connected? Then we can type on at Gmail. Easy to remember. हाँ उस पे भी आप लिख सकते हैं.
can you see that or you can just
Yes.
write
He's typing. Gmail.
oh,
There. To it. Yeah. Any other question? Yes. And the PPT can also be shared with whoever wants it.
Good morning, ma'am. So again, it's not a question. I was very inspired and I was very happy to see that how you sort of, local cuisine event to represent something mathematical. So yeah, thank you for introducing that to us, and it was very inspiring.
Thank you. Um, I think I forgot to mention when we initially also when we did it in our own campus and we invited students from different schools, we would also obviously invite teachers and at least a couple of teachers from each school. The teachers were also always very appreciative and they enjoyed it. They often say that we learned a lot from it. I have been involved in some teacher training also in the past at the like the College of Education in Srinagar, where we had done workshops for school teachers, math, who taught math. And one of the complaints that you would often hear from teachers, it wasn't a complaint. I mean, they were talking about the sort of the real life situation was a lack of resources that when they come to these teacher training workshops, there are often these ideas and so on that are floated, but it's hard for them to implement it because, number one, and somebody had talked about it yesterday or day before, is that the, every teacher has the sword hanging over their head, which is the syllabus, completion of syllabus, right? There's a limited time that's allotted to teachers to complete the syllabus. And in Kashmir, it becomes even more difficult because of the situation we're in. There are a lot of days that are lost because of one thing or another. The second part was that a lot of these teachers are not actually teachers with a math background. They would be teaching class 8, class 9, and some Urdu teacher teaching math and that sort of thing. Which is why the math festival appeals to the teachers because it doesn't take time away from their classroom. It is one day or half a day maybe once a year or maybe twice a year, which is done outside the classroom. So the teachers appreciate that this is something they can do without uh, it impinging on their time, the classroom time. I, I mean, it's not related to your question, but I had heard a very good phrase once, which is that it's not about covering the syllabus, it's about uncovering it, which we tend not to do. We're just so worried about covering it. Uh, Does that answer your question? Okay.
People in the back.
I can hear you in case the mic doesn't work, and then I can repeat your question. Okay.
Good morning, this is Vaishali Silvia. I'm representing Lotus Valley International School right now. We belong to Gurugram itself. It was indeed an enriching session and inspiring too. I'm so overwhelmed looking at the kind of the video that you showed. There was a clip when you just pulled out a paper and then there was some design that actually
Yeah,
caught my
it,
eye.
it's a video. Yeah.
I'm sure it caught some other people's eye as well. Yeah, we were wondering one, we need a little more insight on that. What was it
Sure.
actually? And two, if we want to host such kind of, maybe a teacher training program or something of the sort, how do we reach you? Through the email or?
Through the email.
Thanks.
Yes, thank you. So the question was, when I showed you the reel at the end, I thought everybody does reels on Instagram now, so I should do one also. This is the last math festival that we had done in South Kashmir. But there was a clip, part of the clip where somebody was pulling out this beautiful pattern and it expanded. So the question was, what is that about? And then also secondary, which is if whether I would be happy to host a teacher training workshop in this. I'd be happy to if somebody wants me to do that. But in terms of that video, we were showing, as I said, we often show their videos also. And this was the one before where the tile sort of fell. That is about Penrose tiling and where we talk about symmetry and self-symmetry. So there is a very nice video about Penrose tiling. But the second one with the pattern, it is something called meta materials. I'll write it here. Meta materials. Um, if you have a, say, a piece of, some rubber sheet and you stretch it, say in this direction. So let's say it's rectangular and I elongate it. What happens to the height or the width? It decreases, right? So when you stretch it, one way you're able to stretch it and make it longer, but the other way it gets shorter. Metamaterials were invented recently by someone uh, who was from, I mean, his background was from Iran, and he was inspired by all the, the Islamic art and the geometric art that you see all over the buildings in many parts of Iran, in Uzbekistan, in Kashmir also. Where you have these geometric patterns and the symmetries of those patterns. He used them to create this super stretchy material, which is called metamaterial. That when you stretch it, if you remember seeing that, when you stretch it this way, it also expanded in the other direction. So it doesn't shorten, it expands in all directions. Uh, the illustration that you saw there is obviously a big design, it's a cutout. But what they do is they make it at a very, very minute 5 level. And they are saying that this can be used in medicine also for creating like these stents and so on, so that it stretches the way you want it to stretch. Our attempt has always been when we do these programs, the Math Festival and so on, we try to bring some relevant applications also of the idea. For example, with topology, the rubber sheet geometry, Mobius band, and so on. When you talk about knot theory, we often also then illustrate that there was a mathematician, Dewitt Summers, I don't know if you're familiar. he had solved a DNA problem using knot theory, which the biologists had been trying to solve for years and years in their labs. And here's a mathematician who does it with a pencil and paper without using any high-tech equipment. Um, so those kinds of examples we try to give so that they can see that it's even relevant now, not just 3,000 years ago. So metamaterials was an excellent example in that sense that you can use the mathematics of art to actually create something which is very useful. So Google metamaterials, you'll see. It's the, I mean, it's an engineering question how to create that, but the design is such that they're linked together. So when you stretch in one direction, it sort of expands in the other direction also. If you slow down that video, you may be able to see it. But just Google it and you'll see there are videos of. Yeah. No, it expands on all sides. Hmm. Oh, on the computer. I thought you meant the actual rubber strip. Okay. Anything else? Yeah. Well, thank you very much again.
Thank you, ma'am, for this enlightening session. So after this, it's time to refresh and recharge, and it's time for a tea break. And I request everyone to assemble an auditorium after this break for panel discussion. Timing is there in the booklet. Uh, okay, same menu. Yes. Okay, you have to assemble here only after the break. Okay. चेंज कर लो ऑडिटोरियम की जगह सेम नहीं मेन हॉल ओके